Welcome to Hollier's Chemistry Help. Today we're looking at some analytical techniques to help identify an organic molecule. We're going to use a number of analytical techniques, proton NMR, carbon NMR, infrared spec and mass spec to determine the structural formula of an unknown organic compound. So here's the mass spec information. It gives us information about the parent molecule, and the parent molecule, when it's actually put into a flow of rapidly flowing electrons, it will become ionized and also break into fragments. And those fragments that we get are given on the thing here. So we've got 73, 70, 61, 43, 45, 29 and 15. Now, a couple of those fragments we recognise very easily. 15 is going to be a CH3 fragment, and 29 is a CH2-CH3 fragment. The other fragments we'll have to use later on, but we do know that 43 plus 45 is equal to 88, so it's a fair bet that that is the parent molecule broken into two fairly equal pieces. So the mass spec tells us things about what's in there. It doesn't really tell us where they are and how they go together. It's just like getting the pieces for a jigsaw puzzle. Infrared spectrum gives us information about the functional groups. There's two sections to the spectrum. The fingerprint spectrum will really identify very intricate details, but what we're going to be looking at are the troughs, or in fact they're called peaks, into the left side of that 1500 mark. So the peaks are occurring at about 1750, and if we look over at the infrared absorption data, we will see that the C double bond O has an absorption in that wavelength, in that wave range. So we think that there's a C double bond O present. At 2950, we have got two possibilities. It could be an OH in an acid, but it's not very broad, it's quite peaked. So it's really going to indicate that it's a CH bond, and that's pretty darn useless, isn't it? So we're not getting much out of that. But the C double bond O occurs in carboxylic acids, they occur in ketones, they occur in aldehydes, and they occur in esters. So we know that we've got those four that we're looking at. We can cross out carboxylic acid because we've already said there's no very broad peak. So we're down to ketones, aldehydes and esters. And we're going to have to look at other analytical processes to be able to figure out which one it is. So we go to carbon NMR, carbon 13. We see that there's 1, 2, 3, 4 peaks. And that tells us that there's 4 different environments in which the carbon atoms occur. So number 1 environment and number 2 environment are really quite low on the spectrum, and that tells us that they're quite well shielded by electrons surrounding them. And if we look over at the 16 and 21 range, we can see that that fits into the normal carbon-carbon bond. And it's probably what it's going to be. The third environment has got a little less shielding than the first two. And it sits at around 61. So if we have a look at the chemical shift data in our data sheet, we'll see that, where is it? We've got the, looks like an amide, or more likely it's going to be that CO bond. That's in the 50 to 90 group. So we're thinking that there's a CO in there somewhere. And number 4 has got very little shielding. And so that's probably going to be something that's got an O very close to it. And if we look at the things, we've got the possibility of the esters or acids. So we do have that C double bond O bond in there. It's going to be in the esters or acids section. But we've already said that we don't have a carboxylic acid because we don't have that broad trough in the infrared radiation. So it looks like our unknown is an ester. So what we know so far is that the molecular mass is 88. We've got a CH3 fragment. We've got a CH3, CH2 fragment. We've got a C double bond O and a CH. We don't have an OH, so it's not going to be an alcohol and it's not going to be a carboxylic acid. There's 4 carbon environments, and we have a carbon-oxygen bond, a carbon double bond oxygen, and it is an ester. So we know it's an ester, but we've got to actually figure out which ester it is. Let's just draw the generic structure of an ester, and we can use some of the other information to work that out. So what I'm doing here is I'm just rearranging that so that I can say the COO part of it is going to have a mass of 44. That means we can say that the mass of the rest of the molecule is 44, making up a total of 88 for the parent molecule. So that 44, it hasn't got 1 carbon, it hasn't got 2 carbons, it's got 3 carbons. Can't have 4 carbons, otherwise it would be too big. So we know that we've got 3 carbons that go onto that OC double bond O ester part. So the possibilities are, we're going to start off with 3 possibilities. That's all that I could figure out. We've got 1 carbon on one side, 2 carbons on the other, 2 carbons and 1 carbon, 3 carbons and no carbons. And of course we really should be having the H's put on there, but this is a carbon NMR, so I'm not going to bother. So these are all of the possibilities that we have. All of them have 4 carbon environments, and so we need some more information to be able to identify which one of those is our actual unknown. And that's where the proton NMR comes in. In the proton NMR, it tells us that we've got 3 hydrogen environments, and remember that we've always got to be thinking, are we looking at hydrogen NMR or are we looking at carbon NMR? Really think about which atoms you're trying to focus on. So our number 1 has got 3 little peaks on it, a 1 to 2 to 1, which is a triplet. Our 2 is a singlet. And our third one has got a 1 to 2 to 2 to 1. There's 4 little parts to it, which is a quartet. So there's 3 hydrogen environments. One of them's a triplet, one's a singlet, one's a quartet. We look at our suspects that we've got, and let's just look at each of them individually. So we can see that this has in fact got 3 hydrogen environments, so we can tick that. The first carbon has got 3 hydrogens on it, so that's 1 hydrogen environment. Next to it on the neighbouring carbon, there's 2 hydrogens. So that makes a 2 plus 1 triplet. So we've got the triplet, cool. The next carbon, the one over on the right, that's got 1 hydrogen environment and no neighbouring hydrogens. So that's got a 0 plus 1, it's a singlet. And the final carbon has got 2 hydrogens, so there's a hydrogen environment. And in the neighbouring carbons, there's a total of 3 hydrogens. That makes a 3 plus 1, a quartet. So we've got the triplet, we've got the singlet, we've got the quartet, we've got the 3 hydrogen environments. That's a possible suspect. Okay, so let's have a look at our next suspect. There are definitely 3 hydrogen environments. If we have a look at the first hydrogen environment, there's 3 hydrogens on that one, but there's none on the neighbouring carbons, so that's a singlet. 0 plus 1 equals 1, it's a singlet. This one, there's 2 hydrogens, but on the neighbouring there's 3. 3 plus 1 makes 4, so it's a quartet. And the final hydrogen environment, there's 3 neighbouring hydrogens, so that's a quartet. So that's a possibility too. I'm starting to get worried. Okay, so we've got the last option. We've got 3 hydrogen environments. That hydrogen on the right-hand side, I'm not 100% sure about, but let's just have a look at the hydrogen environments. 1 has got 2 neighbours. That makes it a triplet. Yeah, we've got a triplet. The second hydrogen environment has got 3 plus 2, 5 neighbours, plus 1 gives it a multiplet. There should be 6 peaks on it. So we don't have a multiplet, so that tells me that this is not the right choice. We can rule that out. But let's have a look at the third one anyway. We've got 2 neighbours, which should be a triplet. That would make 2 triplets. We haven't got them, so this is definitely not one of the options. So how are we going to differentiate these? That's when we go back to our little old friend, our mass spec. So we're looking at the fragments. We're going to label these A and B. We're going to look at each of them. So CH3, they've both got fragments of 15. CH2CH3, that's 29. They've both got 29 fragments. So I'm going to have a look if I just sort of chop them down the middle, see what those halves are. So let's draw our little lines and add them up. And that tells us that B has got a 45 and a 43, and they're on our things. A does not have that. So we can say that A is not our suspect and B is our unknown sample. Now we always have to go back to the original question. It's asking for the structural formula, and what I've given is the condensed structural formula. So we need to change it into the structural formula. And while we're at it, let's actually try and name it. So we've got 2 parts to it. There's our carboxylic acid part, and that's going to be ethanoic acid. The other part that makes up the ester is the alcohol, and that alcohol has got 2 carbons in it as well, so that's ethanol. So when you're naming it, you turn the ethanol into ethyl, change the ol into ethyl, and the ethanoic acid into ethanoate, remove the oic acid and add O8, and put them together and you get ethyl ethanoate. So our unknown sample was ethyl ethanoate. Hollier's top tips. We're using the mass spec to find the jigsaw pieces to make up the puzzle. We're looking at the overall molecular mass and the molecular mass of the fragments that are created by mass spec. We use our IR spec to indicate the presence of particular functional groups. Our NMR tells us how the puzzle pieces go together. It's telling us what the neighbourhood's like, how they are actually all going together in the pieces. And you get your clues and you put them together to solve the overall puzzle. All of those things work together hand in hand to give us the identification. I hope you've enjoyed this and I hope you understand it a little bit more now.